Okay, next is slide number 12. It is on convolution in frequency domain. Okay, if you still remember in slide number 8, okay, slide number 8 is impulse train sampling. This one is done in time domain form. In slide number 12, it is in frequency domain form. So if you look at slide number 12, the input signal is in triangle form. Okay, and then we have impulse train. Okay, so if you look at this slide, we have our input signal overlap onto the impulse train. So we have our input signal at every omega t. Okay, so why this happen? Again, I'm going to repeat this one again. The carrier signal, your impulse train signal will be carry your input signal. So if you look here, why we have 1 over t? Previously, okay, the amplitude of our input signal is equal to 1. So our amplitude of our impulse train is 2 pi over t. So what happened? We have 1 over 2 pi times 1 times 2 pi over t. That is why you have 1 over t. Okay, we don't have 1 over 2 pi anymore. 1 over 2 pi is just to represent that your input signal must be in periodic times, is periodic signal. Okay, slide number 13 is on sampling theorem. So ST is sampled at every t second. That's why we have x and t, where n equal to 0, plus minus 1, plus minus 2, and so on. So ST is band limited if ST omega equal to 0 for delta greater than omega m. And ST can be uniquely recovered if we sample at the t rate. So basically, omega s greater than 2 omega m is the general equation for the Nyquist rate. If you look at this equation, omega s is your sampling frequency. Omega m is your message frequency. So when we have an equation, for example, xt equal it is not 10t, it is 10 pi t. It is like this. So we have xt equal to 2 cos 10 pi t plus 3 cos 20 pi t. So your first omega m is 10 pi, your second omega m is 20 pi. So omega s is equal to 2 pi over t. T is actually the sampling period. So let's say it is not given in the question. Okay, you can get from your Fs. So Fs equal to 1 over t. So t equal to 1 over Fs. Alright. So sampling period is t must be less than pi over omega m. So in slide number 14, okay, we can see the violating sampling theorem resulting in aliasing. So basically, slide number 14, it is on the sampling it is on aliasing frequency. It is on aliasing. So if you look here, okay, we have our input signal Sj omega, and then we have our impulse train Pj omega. So if you look at your impulse train, the time difference between 0 to omega t, the distance is quite short compared to our previous example. Okay, so again, I'm going to repeat. Impulse train is actually the signal that carry your input signal. Okay, so if you look after we convolve 1 times 2 pi over t times 1 over 2 pi, okay, we have 1 over t. But again, if you look at the distance between 0 and omega 1, the distance is very short. So what happened? Between first and second signal, it will be overlap because of the distance. The distance is very short compared to the previous diagram in slide number 12. Okay, the distance is quite long. That's why first signal, second signal is not overlapping. Okay, so because of this, the overlapping of between two signal resulting aliasing. Why? Because of we already violate the sampling theorem. Basically, aliasing happen when the sampling frequency is too low. Means your aliasing frequency is less than 2 omega m. Alright. So in slide number 15, it is on the ecosystem between continuous time signal and discrete time signal.